station to recharge his batteries. In this example, John Greenbot is a brand new patient. The room is the environment he needs to learn about. From where he is now in the room, he has 4 possible actions: move up, down, left, or right. And his state is a couple of different inputs: where he is, where he came from, and what he sees. For this example, we'll assume John Greenbot can see the whole room. So when he moves up, or any direction, his state changes. But he doesn't yet know if moving up was a good idea, because he hasn't reached the goal. So, go on, John Greenbot, explore. He found the battery, so he got a reward, that little +1. Now, we can look back at the path he took and give all the cells he walked through a value, specifically a higher value for those near the goal and a lower for those further away. These higher and lower values help with the trial and error of reinforcement learning, and they give our agent more information about better actions to take when he tries again. So, if we put John Greenbot back at the start, he'll want to decide on a policy that maximizes reward, since he's guaranteed another +1. But that's too easy, and kinda boring if John Greenbot just takes the same long winding path every time. So another important concept in reinforcement learning is the trade-off between exploitation and exploration. Now that John Greenbot knows one way to get the battery, he could just exploit his knowledge by always taking the same 10 actions. It's not This 10 action path is also pretty inefficient. There are probably more efficient paths out there, so exploitation may not be the best strategy. It's usually worth trying lots of different actions to see what happens, which is a strategy called exploration. Every new path that John Greenbot takes will give him a bit more data about the best ways to get a reward. So let's let John Greenbot explore for 100 actions, and after he completes a path, we'll update the values of the cells he's been to. Now, we can look at these new values. During exploration, John Greenbot found a shortcut, so he knows a path that only takes 4 actions to get to the goal. This means our new policy, which always chooses the best value for the next action, will take John Greenbot down this faster path to the target. That's much better than before, but we paid a cost. Because during those 100 actions of exploration, he took some paths that were even more inefficient than the first 10 action path, and only got a total of 6 points. If John Greenbot had just exploited his knowledge of that first path for those 100 actions, he could have made it to the battery 10 times and gotten 10 points. So you could say that exploration was a waste of time. But if we started a new competition between the new John Greenbot, who knows a 4 action path, and his younger, more foolish self, who knows a 10 action path, over 100 actions, the new John Greenbot will be able to get 25 points because his path is much faster. His reinforcement learning helped. So, should we explore more to try and find an even better path? Or should we just use exploitation right away to collect more points? In many reinforcement learning problems, we need a balance of exploration and exploitation, and people are actively researching this trade-off. These kinds of problems can get even more complicated if we add different rewards, like a +1 battery and a +3 bigger battery. Or there could even be negative rewards that John Greenbot needs to learn to avoid, like this black hole. If we let John Greenbot explore this new environment using reinforcement learning, sometimes he falls into the black hole. So the cells will end up having different values in the earlier environment, and there could be a different best policy. Plus, the whole environment can change in many of these problems. If we have an AI in our car helping us drive home, the same road will have different people, bicycles, cars, and black holes on it every day. There might even be construction that completely reroutes us. This is where reinforcement learning problems get even more fun, but much harder. When John Greenbot was learning how to navigate on that small grid, cells closer to the battery had higher. But for many problems, we want to use a value function to think about what we've done so far and decide on the next move using math. For example, in this situation where an AI is helping us drive home, if we're optimizing safety and we see the brake lights of the car in front of us, it's probably time to slow down. But if we saw donuts in the street, we want to stop. So reinforcement learning is a powerful tool that's been around for decades, but a lot of these problems need a ton of data and a ton of time to solve. There have been really impressive results recently thanks to deep reinforcement learning on large-scale computing. These systems can explore massive environments in a huge number of states, leading to results like AIs learning to play games. At the core of a lot of these problems are discrete symbols, like a command for forward or the squares on a game board. So how to reason and plan in these spaces is a key part of AI. Next week, we'll dive into symbolic AI and how it's a powerful tool for systems we use every day. See you then. Crash Course AI is produced.
Alright, so that was our first video about reinforcement learning. So if we go with where is it? The little bot guy. So you know how he found this really sort of like long 10-step path? You know, he already found a path to get to the battery. So if they're trying to get the maximum amount of the batteries or whatever they can get in 100 steps, he could just exploit this, and then he could reuse this path as many times as he can in those 100 steps, because he already knows it will lead to the battery. And then, so that's exploitation. And then the second thing he talked about was exploration, which was when the little bot, it like went around a different path to explore to see if you could find there were some moments where during exploration he would take long paths where it goes like all the way around like that, and it wasted a lot of his steps. But in the end, if you were to take the what do you call it, a John Green bot that already found the 4-step path using reinforcement learning compared to a newer one who would have to first explore to find the battery and then he could exploit it, then the one who went through reinforcement learning would be more efficient because it knows the fastest path already. So that was exploitation, exploration. Are there any more questions? Okay. There's also a second video.
From the amazing some vintage
Okay.
From the amazing results in vintage Atari games, DeepMind's victory with AlphaGo, stunning breakthroughs in robotic arm manipulation, and even beating professional players at 1v1 Dota, the field of reinforcement learning has literally exploded in recent years. Ever since the impressive breakthrough on the ImageNet classification challenge in 2012, the successes of supervised deep learning have continued to pile up. And people from many different backgrounds have started using deep neural nets to solve a wide range of new tasks, including how to learn intelligent behavior in complex dynamic environments. So in this episode, I will give a general introduction into the field of reinforcement learning, as well as an overview of the most challenging problems that we're facing today. If you're looking for a solid introduction into the field of deep reinforcement learning, then this episode is exactly what you're looking for. My name is Xander, and welcome to Archive Insights. So at NIPS 2017, Peter Abil gave a very inspiring demo in front of a large audience of some of the brightest minds in AI and machine learning. So he showed this video where a robot is cleaning a living room, bringing somebody a bottle of beer, and basically doing a whole range of mundane tasks that robots in sci-fi movies can do without question. And then at the end of the video, Peter revealed that the robot's actions were actually entirely remote controlled by a human operator. And the takeaway from this demo, I think, is a very important one. It basically says that the robots we've been building for decades now are physically perfectly capable of doing a wide range of useful tasks, But the problem is that we can't embed them with the needed intelligence to do those things. So basically, creating useful state-of-the-art robotics is a software challenge and not a hardware problem. And so it turns out that having a robot learn how to do something very simple, like picking up a bottle of beer, can be a very challenging task. And so in this video, I want to introduce you guys to the whole subfield in machine learning that's called reinforcement learning, which I think is one of the most promising directions to actually get to very intelligent robotic behavior. So in the most common machine learning applications, people use what we call supervised learning. And this means that you give an input to your neural network model, but you know the output that your model should produce, and therefore you can compute gradients using something like the backpropagation algorithm to train that network to produce your outputs. So imagine you want to train a neural network to play the game of Pong. What you would do in a supervised setting is you would have a good human gamer play the game of Pong for a couple of hours, and you would create a data set where you log all of the frames that that human is seeing on the screen, as well as the actions that he takes in response to those frames. So whether he's pushing the up arrow or the down arrow. And we can then feed those input frames through a very simple neural network that at the output can produce two simple actions. It's either going to select the up action or the down action. And by simply training on the data set of that human gameplay using something like backpropagation, we can actually train that neural network to replicate the actions of the human gamer. But there are two significant downsides to this approach. So on the one hand, if you want to do supervised learning, you have to create a data set to train on, which is not always a very easy thing to do. And on the other hand, if you train your neural network model to simply imitate the actions of the human player, well then by definition, your agent can never be better at playing the game of Pong than that human gamer. For example, if you want to train a neural net to be better at playing the game of Go than the best human, then by definition, we can't use supervised learning. So is there a way to have an agent learn to play a game entirely by itself? Well, fortunately, there is. And this is called reinforcement learning. So the framework in reinforcement learning is actually surprisingly similar to the normal framework in supervised learning. So we still have an input frame, we run it through some neural network model, and the network produces an output action, either up or down. But the only difference here is that now we don't actually know the target label. So we don't know in any situation whether we should have gone up or down because we don't have a data set to train on. And in reinforcement learning, the network that transforms input frames to output actions is called the policy network. Now, one of the simplest ways to train a policy network is a method called policy gradient. The approach in policy gradients is that you start out with a completely random network. You feed that network a frame from the game engine, it produces a random output action, either up or down. You send that action back to the game engine, and the game engine produces the next frame. And this is how the loop continues. And the network in this case, it could be a fully connected network, but you can obviously apply convolutions there as well. And now, in reality, the output of your network is going to consist of two numbers, the probability of going up and the probability of going down. And what you will do while training is actually sample from the distribution so that you're not always going to repeat the same exact actions. And this will allow your agent to sort of explore the environment a bit randomly and hopefully discover better rewards and better behavior. Now, importantly, because we want to enable our agent to learn entirely by itself, the only feedback that we're going to give it is the scoreboard in the game. So whenever our agent manages to score a goal, it will receive a reward of +1. And if the opponent scored a goal, then our agent will receive a penalty of -1. And the entire goal of the agent is to optimize its policy to receive as much reward as possible. So in order to train our policy network, the first thing we're going to do is collect a bunch of experience. So you're just going to run a whole bunch of those game frames through your network, select random actions, feed them back into the engine, and just create a whole bunch of random Pong games. And now, obviously, since our agent hasn't learned anything useful yet, it's going to lose most of those games. But the thing is that sometimes our agent might get lucky. Sometimes it's going to randomly select a whole sequence of actions that actually lead to scoring a goal. And in this case, our agent is going to receive a reward. And now a key thing to understand is that for every episode, regardless of whether we want a positive or a negative reward, we can already compute the gradients that would make the actions that our agent has chosen more likely in the future. And this is very crucial. And so what policy gradients are going to do is that for every episode where we got a positive reward, we're going to use the normal gradients to increase the probability of those actions in the future. But whenever we got a negative rewards, we're going to apply the same gradient, but we're going to multiply it with -1. And this minus sign will make sure that in the future, all the actions that we took in a very bad episode are going to be less likely in the future. And so the result is that while training our policy network, the actions that lead to negative rewards are slowly going to be filtered out, and the actions that lead to positive rewards are going to become more and more likely. So in a sense, our agent is learning how to play the game of Pong. Now, I know this was a very quick introduction to reinforcement learning, so if you want to read up a bit and spend a little bit more time in thinking about the details, I really recommend to read Andrej Karpathy's blog post.
I think that's as much of the video that's really relevant to what we're learning about, because the rest of it, he goes into more detail about some other things, and as you can tell, he talks about, like, are robots taking over now? So that was another video, and you can, I think we are also talked about this during our first class. We talked about neural networks, I'm pretty sure. And I think we're going to learn that class 7. So if you guys didn't completely understand what he was talking about towards like the end of the video, that's fine, because we're gonna go into more detail about that later on. But I just want to make sure that you guys really like understand the concept of reinforcement learning. So do you guys have any more questions about the 2 videos we just watched? Because I was also thinking I could show the video from the first class one more time.
Hello, Grace.
Because,
Yeah, I think today the topic is pretty difficult. Maybe we just slow down, just explain some basic concept again. So yeah, I think this is a very difficult subject. Maybe a little bit of slow down is better, okay?
Okay. All right, so then we can go back to this video. So can somebody try to summarize what reinforcement learning is?
Yeah, it's okay. Student can chat if you don't want to speak. Yeah.
Okay, Helen, do you want to type out your question? Sorry, Helen, I can't really understand what you're saying right now, so if you could type into the chat, that'd be pretty good.
Hello, Helen, you want to talk? We cannot hear you.
All right, so what is this more, okay. How do we know, okay, so in a more complex situation, how do we know if the AI did the right step? So in reinforcement learning, there are there's this factor called a reward. So whenever the AI reaches, so like in this example, whenever the bot reached the thing, which was the battery, I'm pretty sure, that was the reward. So it was sort of like telling like, keep going to the reward. And then eventually after we started like, we took the explore path and we explored more of the area. Let me see, I'm gonna try to find the frame with it. But basically we like assigned a number to each section of the grid. And the closer the bot was to the battery, the larger the number was. So then eventually the robot just learned to sort of go to the largest number it could from where it was standing. So I'm not sure if I can find the exact frame with it. I think it's, yeah, so this is where the battery was. I think the robot started here. So then we would go to the biggest number from there and we keep going like that. Yeah, but in like more complex situations, it would just like be the same idea, but on a grander scale, you know? We would basically just, we would like assign bigger numbers to when it's closer to whatever it's trying to reach. So like, even if this is like a bigger grid or if there was like a +3 battery here, the numbers would be bigger around the +3 battery. I think he also shows it like later on here. I don't really know exactly where it is. But it's just the same concept. It's just oh, the black hole like here. They're so if he's moving from left to right, they're also, you notice how they're like negatives? They're saying basically just don't go there because there's like the black hole there. So we just assign even lower numbers there, and eventually I think that it would just learn to not go to this spot over here, and we'll learn to go around. Like you can tell the numbers get bigger like when we go over here, and it's even bigger over here because we went around to go to the +3 battery. But it's smaller over here because the black hole is blocking it. Does that answer your question? Or what are the numbers based on? I'm not really sure myself because I'm still learning about this too. But definitely something. I think the most important thing to understand is that if you're closer to the reward, unless there's something like a giant black hole standing in front of it, the numbers are bigger. And then even though it's like the same distance away from the +3 battery, this one's obviously going to be smaller because the black hole is blocking the way. It wants to stay away from the danger. Yeah, basically. It doesn't sound very efficient when you put it that way, but sort of just like how over here he was talking about if you took the robot that did the reinforcement learning and then you took another one that didn't do it, eventually the one who did the reinforcement learning, even though it went through a lot more steps and took more time to find the shorter path that was like 4 blocks or something, it would be the most efficient robot compared to one who was just exploring once, trying to find the battery, and then from there it just exploits that path over and over again. Yeah.
Okay.
Mhm. And Helen, that's a good question about what the numbers are based on. So I'm gonna try to figure it out and maybe I can share next class. Or if you want to try figuring out yourself too and share it with us, that'd be great too.
I think the numbers have to do with like the maybe like getting to the battery. Like maybe the
Mhm.
bigger the number, the closer you are to the battery.
Definitely. I think what Helen's saying is, how did we get this specific number? Like, of course, the number is going to be bigger to get to the battery, but I think she's wondering, why is this number 0.5? Why is it not like 0.75? And why is it 0.33? So yeah, that's an interesting question. I'm going to figure that out and then share it next class.
Oh,
But
so
yeah.
I think it's because the 0.5 block. So there's no blocks in between it and the battery. So there's 2 blocks. So because they're next to each other, so it's like 1/2. And then because like the 3 blocks for the 0.33. So maybe that could have been like 1/3 or something like that. Because then it's like 3 blocks and it's so like 3 blocks. And then so 1/3 is 0.33. And for the 0.25 and 0.2 and 0.17.
That's a good observation. I think you might be right, actually. But I think it's not based off where the bot's standing. I think it's based off of just this block. So like, we know that 0.2 is 1/5. So then it's 1, 2, 3, 4, 5, right? I'm not sure if it's the same for this one though, because why would it be 1.08? Unless that's just something with the multiple of 3 over here. And then also why are there negatives here? Could be because of the black hole.
Yeah, I think it's because of the black hole.
Yeah, probably. Yeah, I think you might be onto something. I think that might be it. So I'm gonna try to take a look at that later to see if you're right, and then I'll confirm your theory next class. All right, so does anyone have any final questions, comments, or any more theories on how these numbers are determined? All right, well, yeah, so that was what we were supposed to learn today. I like the conversation we had at the end, and you guys had a lot of interesting questions today. And as you can tell, I'm also learning myself, so it's great that we were able to learn together as a class all together. And don't be scared to ask any questions, because as you can tell, these questions are all helping us learn. And it's not just you guys that are learning, it's also me. So yeah, so I think that's it for today, unless someone wants to step in with that. Yeah, I think that's it for today then.
Okay, thank you. Good class.